All right, guys, welcome to lesson 22. In this section, we're going to talk about logs, which are the inverses of exponentials. So a logarithm, or log for short, is another way of writing exponents. A logarithm with base 10 is called a common log and can be written without a base. So you can say log base 10 of x, or you can just say log x. If it's any other base, you got to write it. And then a logarithm with base e is called a natural log, and we can say log base e of x, but we never do that. You technically can, or what we usually do is say ln of x. All right, a logarithm is the inverse exponent. All right, the caveat is that we are able to rewrite exponents in multiple ways. So what does this mean? So from the previous lesson, we talked about exponential equations where we had y equals a to the x. Well, with logs, I can rewrite that. And so if I have x equals a to the y, I can rewrite that as y equals log base a of x. So I bring the y down, and it's log of the base of x equals y. All right. So that may seem convoluted now, but let's give this a shot on number one. All right. So on number one here, I'm going to take the base 5, and I'm going to raise it to the thing on the opposite side of the equal sign, 2. And so x equals 5 squared, which is 25. Okay. All right. B cubed equals 64. And I can take the cube root of that and find out that B is 4. All right. On 3, I can say 3 raised to the y power is 7. Now, we can actually solve this, but we don't know how to do that yet. So for right now, I'm going to leave that alone. All right, b raised to the second power equals 25. All right, so I take the square root, and b equals 5. Now, normally when I take the square root, I would say plus or minus 5. But you can't take you can't take a log of a negative number, right? Because negative numbers are not in the domain. We'll look at the graph of a log in just a second, towards the end of this lesson, and you'll see what I'm talking about. But negative numbers are not part of a log. So I only include the positive answer here. All right, now on 5 through 8, we're going to go in the other direction and rewrite these exponential equations as logs. Okay, so I'm going to write the log. The big number 12 is going to be my base. X equals 2. All right. Log base b of 8 equals 3. So you're equaling the exponent. Okay. All right. Log base e of 9 equals y. Now, I told you we don't typically write it this way, so if you wanted to, you could say natural log of 9 equals y. Either one is correct. We just don't typically see log base e anywhere. All right. Log base 2 of x equals 5. All right. So there you go. Now, we have some properties that we can use to simplify this stuff even further. So we have anything raised to the 0 power is 1, and anything raised to the first power is itself. Okay, so I can apply the same thing with logs and natural logs. So if I have the natural log of any base to the 1, it equals 0. And any log of some base to itself or of itself is also 1. The natural log of 1 is 0. The natural log of e is 1. And then inverses, if you have b raised to the log base b of x, this cancels out and you're left with x. E and the natural log cancel each other out, and so the x comes down and you get x. All right. Same thing here. The log base b of b to the x. All right. All that cancels out and you're left with x. All right. This goes away and you're left with x. Okay. So knowing that, let's get to work. The other thing that you want to know is that if the bases are the same, we can use one-to-one property, which means if even if it's not there to begin with, if I can work to get base b on both sides raised to some power, the powers can be different. But as long as the bases are the same, then I can drop the bases and work with the exponents. So if b raised to the x equals b raised to the y, then I can drop the b's and say x equals y. And if I got the same log to the same base of x and y, then I can drop the logs and work with x and y again. All right, so here's the idea. Number 9, this is going to be 3 to the some power x equals 81. Okay, well now this is where we use the one-to-one property. All right, so I would say 3 to the x equals 3 to the fourth. And you would either need to know that or you would need to work to get that 3 to the fourth. And now that everything's in base 3, I can drop the bases and work with the exponents, and x equals 4. It's helpful if you can write this to a decimal, so 0.04 is actually the same thing as 1 over 25, and your calculator can help you with that. So this would be 5 to some power x equals 1 over 25. Well, a couple things here. I know that 5 to the x, I know that this is 1 over 5 squared. All right, but in order for that 5 squared to come up, I would need to change that exponent to a negative. So this would be 5x equals 5 to the negative 2. Now that everything's in base 5, I can drop the bases, and I get x equals negative 2. All right, number 11. So I got 1/2 raised to some power equals 8. And I know that, first of all, I need to get the 1/2 to be a 2. So this would be 2 to the negative x equals 2 cubed. And now I can drop the bases and say negative x equals 3. So x equals negative 3. 12, 9 to some power equals 3. All right, so I would say 3 squared to make that 9 a 3 equals 3 to the first. All right, and so when you raise the power to the power you multiply, this would be 3 to the 2x equals 3 to the 1. All right, drop the bases, you get 2x equals 1, and therefore x equals 1/2. If you were paying attention back when we were dealing with radicals and fractional exponents, you would, as soon as you write that 9 to the x equals 3, you might already know what's about to happen. Number 13, so we got 2 to some power equals 32. Well, I happen to know that 2 to the 5th power is 32, so x equals 5. Okay. 14, we got 3 to some power equals 1. Well, this is one of our properties we talked about up here. If we have 3 to some power, it's right here. We have something raised to the 0 power is 1. So this would be 3. If you're doing the one-to-one property, this would be 3 to the 0, and so x equals 0. But you don't have to do this middle step here if you understand that property. 15, you got 4 to some power equals 2. Well, this is very similar to this one over here at 12. This would be 2 to the 2x equals 2 to the first. And so you got 2x equals 1, so x equals 1/2. Again, if you recognize it early on, you don't have to do all the steps. All right, so on 16, we got 10 raised to some power equals 1 over 100. All right, so it's going to be 10x equals 10 to the negative 2, so x equals negative 2. The more of these you do, the easier this becomes. All right, so here on 17, you got 6 to the x equals 1. We already did one similar to this. Anything raised to the 0 power is 1, so x equals 0. You can show the extra steps if you want to, or if you need to, but if you know the properties, you're all good. So you got 5. On 18, you got 5 to some power x equals 1 over 125. 5 cubed is 125, so I know this is going to be 5x equals 5 to the negative 3. And it's negative because of the fraction, and I want it out of the fraction. And so x equals negative 3. All right, switching gears, let's talk about e and base 10. All right, so we got 10 to to some power equals 10,000. Well, the beautiful thing about 10 is every time you raise it to a different power, you add a 0. So how many zeros do I have in 10,000? 4. So this is going to be 10x equals 10 to the 4th. So that's going to be x equals 4. All right. The only thing you need to do on 20 is you need to take that e and bring it up. So it's going to be e to the negative 1. And then we know that this goes to 1. And so my answer is going to be 1 times negative 1, which is just negative 1. Essentially, I'm left with whatever this exponent is. Okay? So that's my answer. On 21, e raised to ln. All right, that goes to 1, and I'm left with that exponent. So 5 is my answer. 22, ln of 1, this is 0. So I got 0 over 3, and anytime 0 is in the top of a fraction, my answer is 0. All right, this is going to go to 1. So you got 2 times 1, which is 2. Okay, we're really cooking with gas now. All right, so here, ln of e goes to 1. So I'm left with that exponent, 1/3. All right, on 25, this is 0. So anything times 0 is 0. All right, this goes to 1. So I'm left with that number out front, 3/4. All right, 27, this goes to 1. So I'm left with that exponent 7. And that's my answer. All right, and we kind of went through that kind of quickly, but you can always pause the video, go back and look at it some more. On 28, we know from the properties in the box above that this is going to go away, and I'm left with that exponent. So this is 10. On 29, again, from the properties in the box, we know this is going to go away, and I'm left with the exponent of 3. So my answer is 3. On 30, I know all this is going to go away, and I'm left with this. So my answer is going to be k plus 1. All right, I mentioned earlier that we would look at the graphs of logs. All right, so the logs, all right, the form is log base b of x, where b is the base. All right, it has all these properties. It has all these transformations that are very similar. All right, so we have our parent graph of log base 3 of x, and then we have all these different transformations that are going on. And so we're going to we're going to move over to Desmos and take a look at each of these. So we have log base 3 of x plus 2. I mean, you can kind of tell what's going on just based off the graph here, or based off this box of transformations, but I want to show it to you. So I'm going to move over to Desmos. All right, so we have our parent graph here, and as you can see, as I said earlier, we have x cannot be negative when I'm dealing with logs. All right, it's on the positive side, so any negative x is not in my domain, which earlier, that's why I was able to just stick with the positive square root. All right, so for 31, all right, we have our original graph here, and then if I turn that one on, you can see that it moved 2 places to the left. All right, on 32, you can see that it moved up 2 units. If I look at 33, you can see that it went down 2 units and right 3. And if I turn on 34, you can see that it flipped over the x-axis and it went up 4. So if I got rid of the 4 here, you can see that it just flipped over the x-axis. But once I put that 4 in, it moves back up 4. Okay, so let's go back to our problems. So on 31, all we're doing is we're going left 2. On 32, we went up 2. On 33, we went down 2 and right 3. And on 34, we went up 4. And then we reflected over the x-axis. Transformation is not as bad as people make them out to be, so don't get super nervous about them. All the parameters act the same way. If you're inside the function, it acts one way. If you're outside the function, it acts another way. All right, it's just a few things you need to commit to memory, and then you're off to the races. All right, so that's it for this lesson. I'll see you in the next one.